Hello, this presentation is an introduction to Bezier curves, in particular degree 3 Bezier curves. We'll concentrate mostly on degree 3 Bezier curves in this sequence of videos. Bezier curves are used for modeling smooth curves especially, but more generally smooth shapes with polynomial curves. So we'll have a curve in Rn for some n, and we want to approximate it or get something about that shape with polynomial curves, because polynomial curves will be easy to work with and have good properties. They were, in particular, we'll specify a curve with control points that we call that because they control the curve, and a relatively small number of control points will be used to specify a complete smooth curve. If necessary, we'll put together multiple pieces of smooth curves to make one longer curve. These were developed originally by Pierre Bezier in the early 60s, who was working at the car maker Renault, and they were wanting to have mathematical ways to describe the shapes of the car bodies. Earlier, there was mathematically equivalent things by Paul de Castelgau in the late 50s, who did something very similar at Citroën, another French car maker, again, to specify shapes and so on in the mathematical fashion. De Castelgau was not allowed to publish his work, and so it wasn't known for a while. Bezier did publish his work. The curves are named after him, but as we'll see actually in a future presentation, the algorithms and methods that de Castelgau used are really quite nice. So I'm going to talk very briefly about degree 1, degree 2, and then we'll focus in on degree 3 curves. So, degree 1 Bezier curve. It has two control points, which I'll call P0 and P1. And the curve, we define Q of u to be 1 minus u times P0 plus u times P1. In other words, it's the same as lerp P0, P1, u. And these points, I should have said earlier, live in some ambient space Rn. So as u ranges from 0 to 1, which is the usual domain for Bezier curves, Q of u traces out the line segment from P0 to P1. So the picture here is P0, P1. Here's the curve, as it were, Q of u. It's just a straight line segment. It's not actually curved. Q of 0 is P0. Q of 1 is P1. And as u varies from 0 to 1, the position, the value of Q of u, ranges along the line segment from P0 to P1. So in particular, Q of u is a member of Rn. It traces out the line segment from P0 to P1 Rn. And this is a degree 1 Bezier curve. A degree 2 Bezier curve has 3 control points, which I will call P0, P1, and P2. Again, they're members of some space Rn, n is greater than or equal to 1, it makes a lot of sense even to talk about curves in R1 because they're useful for lots of things. And the picture is something like the following. We've got 3 points, P0, P1, and P2. And if we join them by straight line segments, these straight line segments are called the control polygon. So this and this segment together are the control polygon, and the curve Q of U looks something like this, with Q of 0 equal P0, Q of 1 is equal to P2. So in other words, it starts at the first control point, P0, it ends at the last control point, P2, and the curve is happening for U in the range 0 to 1. We trace out a curve that looks something like this. So it starts at P0, it ends at P2. In the middle, essentially think of the curve being pulled towards P1. So in this picture, it's bowing up from P towards P1, and we get this smooth curve going from P0 to P1. And you'll notice here we actually have some tangency. It's tangent to the control polygon at the endpoints. So that's here, and also it's tangent here. The formula for this is Q of U equals 1 minus U squared times P0 plus 2 times U times 1 minus U times P1 plus U squared times P2. And if you do a little bit of calculus work, you can see that you have all these properties that I was talking about here, starting at P0, ending at P2, and having the tangencies to the control polygons. So this is a degree 2 curve. Already it gives you a fair amount of flexibility to build curves, but we get more flexibility with not much extra work by going to degree 3, and I'll talk about that next. A degree 3 Bezier curve has 4 control points, which I'll call P0, P1, P2, P3, and again, they're all in Rn. And the formula for this, I'll do that first, is Q of U equals 1 minus U cubed P0 plus 3 times U times 1 minus U squared times 1 plus 3 times U squared times 1 minus U times P2 plus U cubed times P3. And this is done, we're typically interested in the values of U between 0 and 1. So notice that this whole thing, Q of U, is a point in Rn, and as U varies, the values of Q of U trace out a curve. And what it looks like is something like the following. I'll just do one configuration of points for the moment. Here's P0, here's P1, here's P2, and here's P3. We'll join them with straight line segments. And these are the control polygon. And the curve itself looks something like the following in this case. It starts at P0, it ends at P3. So here's Q of U, for 0 less than or equal to u less than or equal to 1. Q of 0 equals P0. Well, that's just immediate from the equation because we put 0 in for u. This coefficient is 1. The remaining coefficients are 0. Q of 1 is equal to P3. Okay, so that's this point here. And we have the initial and final tangencies. So Q of u is tangent as a curve. It's tangent to the control polygon. It's in this at its initial and final points. That is, in other words, at u equals 0 and at u equals 1. And that's drawn here. So we have a tangency here. It's supposed to be tangent to the control polygon, and another tangency here, tangent to the control polygon. So just to give these things some names, these three values here, these coefficients, are called Bernstein polynomials, or you can also use the named after mathematician Bernstein. They can also be called blending functions, or basis functions. They all happen to start with B. But they give you a weighted average. The point here is they express Q of u as a weighted average for u between 0 and 1 of P0, P1, P2, and P3. And this is a weighted average as long as u is in the interval 0, 1. I'll do some more examples of this on the next board. I want to give two more examples of how the Bezier curve of degree 3 can look. Here I've got the points P0, P1, P2, P3 organized in a sort of zigzag fashion. They could also be arranged, for instance, in this fashion here with P0, P1, P2, and P3. And then the control polygon, taking them in order, P0 to P1, P1 to P2, P2 to P3. The control polygon will go in this order. And now the curve Q of u will look something like the following. So the point here is Q of u starts at P0. It ends at P3. And we've got tangencies at the beginning and end where u equals 0 and u equals 1 to the control polygon. So although the points are arranged in different order, it's the same kind of thing. And in both cases, you should be thinking of the following, that these middle points, the middle control points, P1 and P2, are pulling the curve towards them. So think of the curve Q as being some flexible, stretchy thing, and these having some sort of pull on them, that's attracting it to them. So you start off firmly at P0. As u increases, you get pulled towards P1, but then P2 starts pulling, so you pull over this way, and then in the end, P3 pulls it all the way back to it. And that's the sort of intuition of how the curve is being formed. Another way you could arrange the points is we can have P0, P1, P2 and P3. And now the control polygon is the straight lines going like this. It's not very straight. So now the control polygon actually crosses itself. And here the Bezier curve can look something like the following. It might even have a little loop there. Could actually do something like this. And we've still started at P0, so here's Q of U is this black curve here. Still, Q of 0 is P0. It starts at P0. Q of 1 is P3. And we still have the tangencies here. So this particular type of curve may not be that useful in practice for modeling surfaces and so on, but these two types of shapes can be used in all sorts of situations to model pieces of curves. Now I want to talk about some of the properties of Bezier curves of degree 3. So let me write the formula first. So here's the formula from the previous board again. And these coefficient functions, these are the Bernstein polynomials. And I'm going to call this one B0 of u. So B0 of u is 1 minus u cubed. This one is B1 of u. So B1 of u is 3u times 1 minus u squared. This is B2 of u, 3u squared times 1 minus u. And this is B3 of u, namely B3 of u equals u cubed. And so some easy properties here are that, first of all, B0 of u plus B1 of u plus B2 of u plus B3 of u is equal to 1. That's easy to do by hand, or you can do something with the binomial theorem to see why that adds up to 1. So Q of u is an affine combination of P0, P1, P2, and P3. Second, for u in the interval 0, 1, each pi of u is greater than or equal to 0. So in this case, Q of u is a weighted average of P0, P1, P2, and P3. And that's easy to check just by the forms of the formulas there. We can also make a little table of values here. So here's B0 of u, B1 of u, B2 of u, B3 of u, and at u equals 0, B0 of 0 is 1, because 1 cubed is 1. The other ones are all 0. And at u equals 1, B3 of u is 1, because 1 cubed is 1. And the other ones are all 0, again, because they have a factor of 1 minus u in them. So this tells us, by this table here, Q of 0 equals P0, and Q of 1 equals P3. So that gives us the starting and ending point of the curve Q. It starts at P0 at u equals 0, and it ends at P3 at u equals 1. We can also do the same type of stuff with the derivatives. So here's the derivative of b prime of b0 of u, the derivative of b1 of u, the derivative of b2 of u, and the derivative of b3 of u. So this is easy calculus computation. I'm just going to let you do this on your own. At u equals 0, the first derivative of b0 of u turns out to be minus 3. You can just plug in here and see that that works. The derivative of b1 of u is positive 3. The derivatives of b2 of u and b3 of u are 0 at u equals 0. On the other hand, the derivatives of b0 and b1 at u equals 1 are 0, whereas the derivative of b2 at u equals 0 is negative 3, and the derivative of b3 at u equals 1 is positive 3. So this tells us that the derivative of q, we just substitute in here the derivatives of p0, p1, p2, and p3 are constant. They don't vary. The only thing that's varying here is the u. So we take the derivative at u equals 0, and we have minus 3 times p0 plus 3 times p1 plus 0 times p2 plus 0 times p3. And this turns out to be 3 times p1 minus p0. And the derivative at 1 is 3 times p3 minus p2. So this is going to give us the tangencies. So this will imply the stuff about the tangencies that I talked about. To illustrate these tangencies, let's redraw a curve. So here's P0, P1, P2, P3. And the control polygon is the straight line segments joining these together in order. And by Q of 0 equals P0, you know the curve starts here. By Q of 1 equals P3, we know the curve ends here. And now the derivative of Q prime of Q at 0 is 3 times P1 minus P0. Well, this is the vector P1 minus P0. Right? Its tail is at P0, its head is at P1. So Q prime is the vector giving the rate of change of Q. And so at 0, its initial rate of change is up this way. Right? It's going fast enough to get to P1 within 1/3 of a time unit. Right? But it quickly goes off like this, and it comes back down like this. And when it comes in, its derivative here, P prime of 1, is 3 times P3 minus P2. In particular, it's a positive multiple of P3 minus P2, and P3 minus P2 is this vector here. So it's coming in at a rate, in the limit, at a rate that would take you from P2 to P3 in 1/3 of a time unit. So that is enough to prove the assertions I made earlier about the tangencies. So this is the definitions and the basic properties of degree 3 Bezier curves. I'll do some examples in the next presentation.